And now, after a quick delay, I have the pleasure to welcome you with a presentation entitled "Is Persistence on Serverless Even Possible? Pwning AWS Lambdas and GCP Cloud Functions" by Paweł Kusiński of Secure Ring. Big applause.
Okay. Hello, everyone. Thank you all for coming. Today talk is gonna be about serverless on. Sorry, the delay. Today talk is gonna be about persistency on serverless environments, on example of AWS Lambdas and GCP Cloud Functions. So, we are going to achieve full persistency and live exfiltration of the data with nearly untraceable method using an RCA vulnerability. And this calculator is the only one today. Our marketing department said that they found some correlation between calculators and security conferences. So here it is. I'm gonna start with why I even choose this topic. My first impression was found in Yuval Avrahami from Unit 42 Security Research about persistency. I hope I pronounced his name right. Second thing is how often function as service is used in corporations. In one third of corporations are using function as service. So I thought, what if there is some kind of vulnerability? What if this vulnerability is a remote code execution? Some of you may think that RCE is non-common thing. But I think we are living in interesting times when things like typo squatting, dependency confusion, or attacks on package managers are a thing. So introducing one to the code is possible. More about it said my friend Mateusz yesterday, so you could probably Google it. But I also found that last week there was in a Pipey malicious Python library, someone added some malicious code to the CTX, which, by the way, extracted AWS role keys. So, let's imagine normal Lambda. Lambda which is processing some data and saving it to the DynamoDB. Let's say our developers were clever ones, so they added an IAM role which could only write to DynamoDB without permission to read it. So, in case of any vulnerability, we won't be able to read the data. But what if we can hijack the data on the Lambda level? What if we will control the Lambda? We could then exfiltrate the data to our server. We don't need the role keys. To get to this moment, let's start from the basics. So, how the serverless infrastructure even work? I wanna say about two topics. The first one is a cold start. Cold start is a phenomenon which makes a first Lambda execution a little bit slower because an environment has to boot up. So, consecutive calls are faster because the environment is already running. I thought at first that the function code is executed in a single sandbox every time, but I was wrong because file system persists between the calls. It is only frozen, so anything what will change between the executions will stay. At least that was my reaction. I don't know if anyone knows it. How it works in steps. First, we have our user or service, which is calling our function. On the backend of AWS, there is some invoke service, which is searching for the environment to execute our function. In case if there isn't one, he's waking one up using Firecracker. Firecracker is a software developed by AWS, which is booting micro VMs. I won't go into that, as this presentation would be too long. But these micro VMs execute our function, which then, of course, sends a response. In case of consecutive calls, it will go faster. The invoke service will just send the request to the right environment. So we can just simple this diagram like that. In case of GCP, the execution is similar. It is just containerization, not a VM. Second thing is a control process. This is name I came up with. That's something what controls our function inside the container or a VM. In case of AWS, we have something like this. So we have a slicer process, which is outside our VM and is sending the events through the shared memory. Then we have running init process, which is called by Bootstrap for the events. In the return, he gives invoke ID, which would be important later. The Bootstrap, after getting an event, is sending it to our Lambda, which then responds to it, and Bootstrap sends a post with invoke ID to end the process. In case of GCP, flow is rather easier, as there is just a web application framework like Flask. And Flask is routing the request to our function. So let's sum up all of this information, why persistency is even possible. First, we have non-volatile file system, at least for a few minutes, as the environment will be killed after, for example, 5 minutes in case of AWS, if none request will come. Then we have writable file system, because we can write to the temporary and to the memory. This is a little lie, but we can use it. Also, we have a control process inside the container, which we can hijack. So our malicious flow would look like that. We will send the malicious event with our payload to the Lambda, which is vulnerable to RCE. Our payload would execute new Bootstrap, and we have to get an invoke ID. We can get an invoke ID from the memory, for example, or we can use a little gimmick from an AWS. If we call an init process again with the next request, the init process responds in invoke ID, because the last call didn't end. And because of that, we are now controlling the Bootstrap, and we can exfiltrate the data live. With GCP, we'll use some other method, as we'll use this little monkey. And to be exact, we'll use process called monkey patching. Monkey patching is dynamically overwriting definition of a function. So our payload is going to overwrite the root function and then again send our payload, our data. So for a demo, I prepared a vulnerable function with an RCE, which is just an YAML RCE. And look how it works. On the right side, we've got an attacker's server, which will be listening for the data. On the left side, we're having an attacker's interface, which will be sending a payload, and normal user interface, which will be sending a valid YAML data. First, let's send some data just for the test that our Lambda is working. Then we have to prepare our payload. We have to start our listener, and then we have to prepare our payload into YAML. After that, we are sending the payload to the Lambda to hijack the bootstrap process. The execution is a little longer, what also could be important later. Now, let's send some valid YAML files to the function. And as you see, our server got also the data. Even on second time, the data is also received. So even if our function don't have read data permissions, we can just exfiltrate the data live. The whole magic is done by this code. We'll go through that, so don't read it now. First thing, we have to decode the runtime. That's in another argument of our payload. Then we are saving our runtime into the file system. In case if file system, at least temporary, is non-writable, we can just create an anonymous file inside a memory, inside RAM. As I said earlier, we can get an invoke ID through the HTTP request to the init process. And at the end, we are executing new runtime. The new runtime is just as a normal bootstrap process with a few changes. First, we have to add the start function, which will get the invoke ID. Then we have this beautiful code, which is non-readable, but we have to just see this one line. This one line is going to execute the exfiltrate data function, which looks like that. This function just sends, using URL lib, the data to our server. URL lib is by default installed on the Lambda environment. Let's see a little bit faster how this works on GCP. So let's start with sending the valid YAML file to the cloud function. Now we are creating, using evil function, a YAML payload. We are starting the listener, and we will be sending valid data to see how it works. And as the last time, we've got our data to our server. The switcher function is similar to the last one. Again, we have to decode our external data and save it to the file system. Then everything changes. As we are using monkey patching, we have to get path of client function, of normally executed function, to overwrite it. Then we're just doing a dynamic import manually by the code. We cannot use import as it won't work. So we are just getting the metadata from the location and then building the module. We have to also append it to the path and add it to the namespace. We can also execute it as we have to build the namespace of our module. What could be interesting for someone is, what is this app? This app is just a current app of a Flask, because we are working inside of the Flask process. So we can just import it earlier and include the data into it. The monkey patching is easy. We are just overwriting the routing function for the run path, which is a default path for executing the cloud function. The new HTTP view func wrapper is our new function which will be executed on the default execution of the cloud function. As the previous time, we are just adding the line of exfiltrating the data. But this time, we don't have an URL lib, so I'm sending it over a socket. If someone wants to try it, I've got a GitHub which contains all the payloads and also vulnerable functions and terraforms to just run it in a one function. I will be sharing the presentation later, so I hope everyone can try to do it. Some of you may ask, what about executing from external process, as this payload was executing inside the same process? In case of Lambda, we don't have any problems, as we are just calling the init process, so we don't have to be able to access memory stack. In case of GCP, as we are doing monkey patching, there is a problem. If we will be in another process, we cannot monkey patch the Flask app. And on current time, I don't found a solution. So if anyone know it, just write me a message. Let's go to the mitigations. We can, in case of AWS and GCP, just move the function to the VPC. Inside the VPC, normally, function won't have an internet connection. So that's just enough, as our function won't be able to call our server. The same works with GCP if we will choose the whole traffic routing option. If we want to have internet access, we can do it by connecting the NAT gateway to the subnet and configuring the security group to not allow any outbound, which in case of AWS is done by default, as we've got implicit deny. In case of GCP, it is a little bit different, as by the default, all outgoing connections will be allowed. So we have to introduce a deny rule for the traffic. I would suggest creating an allow list if you want any connection from your Lambda. And here's an example of AWS security group which won't allow the outgoing connection to our external server. As you can see, I hope, there is a connection timeout. In case of GCP, it would look the same, but we have to introduce the deny rule. And again, we have timeout. So, what about detection? To be clear, there is a little problem. I've got few ideas, but they aren't ideal. We can create an alert based on execution time, because as you saw, the execution of our payload is rather longer than normal execution. But that won't be foolproof, because in case of some problems with our own code, the execution time could be longer, and the alerts will be false. The best thing we can do, I think, is to introduce secure development lifecycle, as we should verify all third-party libraries. We should scan our code. We should deploy our code using some test environments and verify if there isn't any RCE vulnerabilities. I've got idea also to implement some defensive layers which could verify the runtime, but that could be also not so foolproof, and that could be a problematic for the developers' teams. There are also flow logs which will show this malicious traffic, but if we don't know what an IP of an attacker is, we cannot find it. The last thing I wanted to say is how to research functions. So, in case of AWS, we can read the documentation. The problem is, it is hard to find anything in the documentation if you don't know what to look for. AWS documentation is a little bit chaotic, but if we know what to search for example, Firecracker, there's a lot of information about it. In case of Google, documentation is, I would say, rather problematic, as there is a lot, there isn't a lot of information. We can also search for reinvented events and blog posts which describe how it works under the hood. Of course, we can also search for information through Google, or even deploy Lambda locally, as we can find images of both Cloud Functions and Lambdas on GitHub, on official Google and AWS profiles. But the best method could be researching it through the real environment. I've recreated, by basing on Juval's application, a pseudo shell, which is working on the Lambda and also Cloud Functions. We can build it through one command using Terraform, and then execute through it commands on the Lambda. It is based on HTTPS, so it isn't a reverse shell. It will send the command to the serverless environment, execute it, and send back the response. We can also download or even upload the files. So it won't make our bill for $1 million because of execution time, as it is really fast. Again, we can download it from my repository. Thank you for your attention. That's everything I got today. If there is any questions, feel free to ask.
Exactly. If there is a question, I will come up with a mic.
So you said that GCP is using gvisor under the hood, and you said it's containers. So gvisor actually have two modes of operations. It's either using ptrace, and then it's a container directly, but it can also use KVM, so I guess that's a VM under the hood. Do you maybe know which one of those modes do they use?
As I read the Google documentation, as I said, there is not a lot of information. It only said that they are using the containerization, so I think that would be containers, not KVM micro VMs.
Okay, next question.
I have a question regarding how long your injected code will persist on AWS, because we know that if the function will not be invoked for a few minutes or more, your VM will be destroyed. Do you need to execute once again your injected code?
Yeah, that's true. If we are not using the Lambda for about 5 minutes, the environment will be destroyed and our payload will not persist. But if we really want to use this method, we can create, for example, Python script or even some cron script, which will just call the Lambda every 3-5 minutes. So it will then persist.
Okay, next question.
So you said that the outbound firewall rules are the solution, but what if someone work like that? You can cache somewhere the data, for example, in memory or in temp file, and then you can send another request, and you override the returning data with this from the buffer, and it will work.
Could you repeat, because I'm not sure
So
if I understood.
you
You are
lock all the
saving
data
you are saving the data on the memory, yes?
In the memory, yes.
Yeah.
And then you request once again, and for example, somehow you know from which address the request will be, and if the IP matches, you override the data that was returned with the data was locked in the buffer, for example.
Yes, you've got a right point. That probably would be possible, and that probably would just exfiltrate the data. So yeah.
Next question.
But we have, we have to remember to give these consecutive calls to be sure that our file system will persist, because the data could be loose.
And I would like to ask you about Azure, because you showed in AWS and GCP. Is the same issue exist in Azure Functions or not?
I have to say I didn't have time to test Azure. I want to do it later. I would guess that it is possible, but I cannot be sure for now.
Okay, any further questions?
So regarding persistence, can Lambda call itself and live forever?
Lambda, I'm not sure. I think Lambda couldn't call myself. And also calling Lambda all the time would introduce a lot of bills. So it will be noticed fast. So that's not the best method, I think.
Okay, are there any further questions? Okay, I didn't see any. So if you have any different questions you would like to ask in a private, I'm sure Paweł will gladly answer them. And that's a wrap on Confidence 2022. Big applause for Paweł and for all the speakers today.